Hey everyone, so in this video I'm going to go over the review sheet for your test 3 of quarter 2. Okay, so quarter 1, I'm sorry. Alright, so the first example says which of the following has x plus 2 as a factor. Now, you can go ahead and remember that, well, you can divide and see if something's a factor. You can do synthetic division, all of these choices, but the easiest way to do this is to use the remainder theorem. And what the remainder theorem states is if you plug in, like if you set this equal to 0 and you plug in the opposite sign, which would be -2, into any of these choices, and for x, the y value is the remainder. And that's how you would explain it. So you're going to look for when y equals 0. When y equals 0, the remainder equals 0. So think of it as like all of these guys are equal to y, because if x is in there, then y comes out. Okay? So we're finding out what y equals, and you're going to find that out by plugging in the x values. So like for the first choice, I'll plug in -2. You're going to plug in -2 for all of them. When you plug that in, you actually get getting 9. So this means y equals 9, which means the remainder equals 9, if you were to actually divide it out. It's basically a shortcut. That's what the remainder theorem is. I plug in -2 here for all the x values. Just really make sure that you're using parentheses. And you'd end up getting 0. And oh my god, that's your answer, because you want to find the one that gives you a remainder of 0. And if y is equal to 0, then the remainder is equal to 0. But just to reiterate, let's just plug into all of these. And when you get -2 into this, you get 7, which means the remainder is 7. Plug in -2 into the last one. Okay, I'm running out of room. Let's move this over. Okay. Again, remember to use your parentheses, and you'll end up getting -60 for this one. That's your y value, so that means your remainder is -60. So which one has it as a factor? You would say choice 2. They're asking you to explain. And this is because when x is -2, y is equal to 0. And according to the remainder theorem, the y value is the remainder. Okie dokie. Next example. Okie dokie, so for number 2, you're solving, you're subtracting these two guys, and you're going to combine them, but in order to combine radicals, you need to have the same radical. So, if you remember back from the lesson, I dealt with the smaller one. So the smaller radical would be the second one, because it's a 20, not a 45. And you're going to think, well, I'm dealing with a square root, so I want to find the perfect square inside of 20, and that would be 4 and 5. X does not come out, but the square root of y squared is y, so that's good. And the x stays, square root of 4 is 2, square root of 5 stays, square root of x stays, because they're not perfect, but y comes out. And then you're going to put everyone who is outside the radical to the front of the radical, and there you go. So this means that you want 5x inside the other one, and you're going to make that happen. You're going to think, well, if 5's in that one, 5 has to be in this one, and we should know that 9 goes into 5. 9 goes into 45 5 times. And that's great, because we know that 9 is a perfect square. Again, square root of y squared is y, but then you're left with x cubed. Now, if you're doing it this way, you're going to think, what's the highest value below 3 that's divisible by 2, because that's your index? It would be 2. So you're going to break it up into x squared and x, and you're going to end up getting x, square root of x, and y. And then you're going to pull everyone out that's in the front. So 3x and y are all outside the radical, and then 5x is inside. And then now you should notice that this is the same thing as this. All you have to do is do 3 minus 2, and you get 1. So the answer is xy square root of 5x. Okie dokie. Where am I? All right. Dividing radicals. As long as they're the same type of radical, and these are, they're both square roots, you can just divide the insides. So 2 is just going to chill on the outside, and I'll rewrite my radicals because you can kind of see that C5 is smaller than 80. So when you divide 5 by 80 in your calculator, you can use alpha y equals to do this. It reduces to 1 over 16, I believe. And that's what would go in here, 1 over 16. You have x over x cubed. Now, when you divide, you subtract exponents, but you would get 2, leaving you a 2 on the bottom. But if you want to see it all done out, there's 1x on top and 3 on bottom, leaving 2 on the bottom if you cancel out one of them. Same thing with the z's. 3 minus 1 is 2, so you get z squared on the top. But if you want to see it out, z over z, these cancel to get you z squared. Then you'll just take the square root. The square root of 1 is 1, you don't have to write that. And the square root of z squared is z. The square root of 16 is 4. Square root of x squared is x. And then 2 over 4 reduces to 1/2, and you're left with z 2x. Okay, so this page is all solving radical equations. So most importantly, you need to check your answers. So first off, you see that there's a single radical in this one. Make sure it's alone. It is. So you can go ahead and square both sides. These guys cancel. You'll be left with 9x plus 10 equals x squared. Now you should remember that x squared likes to equal 0. These cancel, and you're ending up with 0 equals x squared minus 9x minus 10. And then what you're going to do is AM. So you're going to do x minus 10 and x plus 1, because that's the factors of 10 that add to 9, negative 9 specifically. You're going to get x equals 10 and x equals negative 1 as possible answers. And then you're going to check your answers. Now, I suggest you put this original side into y1 and this side into y2 and look at the table to see which side equals what. Or just plug in. And when you plug in, you'll see that negative 1 doesn't work. It's an extraneous solution, and that 10 does work. So that's your answer. Same process here, except this one is a little bit more tricky because there's 2 n's in this one. So this should say values of n, not x. That's silly. That's okay though. All right, so then I'm going to solve. So isolate the radical. Is the radical isolated? No, it is not, because there is a negative n next to it. So I'm going to add the n over next to the 2, and you'll be left with 6n plus 19 equals n plus 2. It's always proper to put the letters first. You could do 2 plus n, though, if you really want to. Then once you isolate that radical, you can square both sides. This will cancel. The whole goal really is to get rid of the radicals, so once you do that, you're great. Now here, you're not going to do that. That's wrong. You can only do that when there's multiplication in the middle. That's not the case here. You have to write this out twice and do box method. So n2, n2. N times n is n squared. 2 times n is 2n. 2n again, and 4. Okay, so then you would end up getting n squared plus 4n plus 4. And then 6n plus 19. And you're going to solve for n. And you should remember that n squared, or x squared in this, x squared likes to equal 0, but it's n in this case. So I'm going to bring these guys over. You'll end up getting 0 equals n squared minus 2n minus 15. And you're going to end up doing AM. N minus 5. And n plus 3, the factors of 15 that add to 2. So you'll end up getting n equals 5 and n equals negative 3. And you're going to check either by plugging these each in one at a time or going to the table. And in order to do the table trick, you have to plug in this whole side into y1 and then this whole side into y2. And you look at the table and you look at the 2 values that you got here, which were 5 and negative 3, and you'll find out that negative 3 is a no-go. This one does not work. You reject him. We also called this an extraneous solution, and you also might see the answer in brackets like that. Okay, number 6. This is a double radical question. First things first is you want to make sure that the radicals are separated on either side, and that is the case here. So since that's happening, all you have to do is square both sides to start. This will cancel out this radical, and you'll be left with x plus 5. And then over here, you have to do box method because it's a subtraction symbol. You can write it out twice if you want first, but there's no need. 5 times 5 is 25. 5 times negative 1 is negative 5, and then add that square root of x on the end. Same thing here. 5 times negative 1 is negative 5, add the square root of x to the end. A negative 1 times a negative 1 is a positive 1, so really just a 1 goes in that box, but you don't have to show it. And a square root times itself is just its inside. Remember, that's because it's just the square root of x squared, and these would cancel each other out. But there's no need to write that. We should all know at this point that a square root times itself gets you the radicand, which is the inside of the radical. All right, so you end up getting x plus 5 equals 25 minus 10 square root of x plus x. Now here's what happens. Our double radical problem turns into a single radical problem, and your goal is to get this radical alone. And you're going to do that by subtracting the 25 over and subtracting the x over. These will cancel, these will cancel, these will cancel. You'll get negative 10 square root of x, and this will get you negative 20. Solve for x, so you're going to have to start to get that radical alone. This will get you 2 equals the square root of x, and then squaring both sides, you end up getting 4 equals x, because these guys cancel. Again, check, and you'll find out that 4 does indeed work. All right. Last page, people, we made it. So this example here, number 7, gives you a graph. And they said the graph of p of x is shown to the right. And they're saying that p of x is divided by x plus 2. And they want the remainder. Well, if you actually knew the polynomial, I would suggest doing synthetic division. And you would put negative 2 inside the box, because x equals negative 2. This is another remainder theorem problem. You guys should know that since we're looking for a remainder, the remainder is the y value. So I'm going to look at negative 2. That point's here. And that point is negative 2 comma 1, 2, 3, 4. So what's the remainder? The remainder is 4. Because it's the y value. And I don't know why I wrote 5, but it's 4. I know why I wrote 5, because I'm looking at the other question. I'm just skipping ahead. All right, so number 8 is another type of a remainder theorem problem, because look, they're asking you to plug in x equals 5. So you're going to first do that. And you're going to get negative 97. Now what's the connection between part A and part B? This is A, this is B. It says, what does that tell you, this result, tell you about x minus 5? Well, this is interesting. Well, we plugged in x equals 5. How are these connected? Well, if you just subtract the 5 over, you'd end up getting x minus 5. So this is really what this is getting divided by. Okay? So what does this tell you about a factor? Well, since f of 5, oops, that is very messy. F of 5 does not equal 0. X minus 5 is not a factor. The remainder theorem is a beautiful thing. It lets you skip over the whole division process and just state whether or not something's a factor or not. Okay, so algebraic proof. It says algebraic prove that the left side equals the right side. So, or disprove, it says, by the way. So this one is possibly right or possibly wrong. So I'm not going to really touch the right side because the right side looks all combined, but the left side I can expand and multiply out. Okay. You're going to box method this plus y. You'll end up getting x squared, xy, xy, and y squared. And you'll end up getting x squared plus 2xy plus y squared. Now don't forget, this guy is still there. And you're going to box method again. I usually put the smaller one on the left side and the bigger one on the top. You're going to make 3 by 2. Multiply x cubed, 2x squared y, xy squared, x squared y, 2xy squared, and y cubed. And then you're going to combine like terms. These combine, these combine. You'll end up getting x cubed plus 3x squared y plus 3xy squared plus y cubed. And you're going to ask yourself, does that equal the other side that they gave us? And you're going to say, no, it does not. This is disproved. Because this does not equal x cubed plus 3xy plus, y cubed. It looks promising though, because we had these that were the same, but the middle term is, there's two, and then they only give you one. All right. I'm all slanted. All right, last question, completely factor. Now there are two approaches to this. Either you can take the GCF out first, or you can factor first, like by grouping. I don't really know which way you guys want to do, but let's pretend like you didn't see there was a GCF of D in this. Let's pretend that. So you would take out a 2 here and a D cubed. So you'd be left with 2D cubed and then D plus 3. That means you want D plus 3 on the other side. So let's see. Well, these are both negative, so we're definitely going to take out a negative. And, well, I want 3, so I would do like 54 divided by 3, because that's what I want there, and it gives me 18, which that's your GCF. But you could also do the GCD thing in the calculator. If you press math num GCD, you can get the GCF if you do 18, 54 in that thing. D also comes out. Negative 18D. D minus, plus 3, because we're dividing by a negative. Now, these guys come together in one parenthesis, and then the D plus 3 comes together in another one. And now you have to ask yourself, am I done yet? And the answer will be no, because you have to take a GCF out of here. It's a D and a 2. So you'd be left with D squared minus 9. Then you ask yourself, are you done yet? No, this is dots. And now you're done. Do you know how you're done? Well, look at all the powers. They're all just D. There's no squareds. There's no other letter next to the numbers 3. It's all good to go. So that is your review sheet. I hope this helped you, and I'll see you guys soon.